Okay. All right, let's move it to the last panel before the closing speech. And we have problems and solutions. And I'm happy to say that some of the solutions are actually being elaborated here at CU, as you see over there. We are going to have Dr. Michael Guzev, who is a professor associate dean for research at the College of Engineering and Applied Science, which is one of our gems here at CU. And Dave Newport, which is supposed to arrive anytime soon, which is the director of the Environmental Center, also here at CU. And then Greg Dingle is head of sports management. It's one of the co-authors of the Slippery Slope, and is supposed to join us remotely. Let me see if any chance is here. Nope. So we are gonna start with Michael. I'm gonna.
All right. Hi, I'm Mike Guzev. I'm a professor in civil environmental architectural engineering here on campus. I'm also part of the Institute of Arctic and Alpine Research. I have an awesome team of 9 people deployed in Antarctica right now. I'm not one of them, unfortunately. So that's just the way this year went. But I'm a hydrologist. I spend a lot of time thinking about where does water go and what is it carrying with it. And so from that perspective, I've started to think a little bit about snowmaking, and I'm going to bring this back to some research that we do on the Colorado River. So I'm going to, by the end of this, it'll all come together, hopefully, in a nice, pretty package. But I will admit that I got a little inspired by talking to Fed about this a few weeks ago, and have thrown out a hypothesis that I think is true, that I'm gonna walk you through, and we'll see if you guys buy it. But first of all, let's start with the hydrologist sort of view of the world is on the left-hand side. And this is sort of typical hydrology 101. So we say precipitation comes in, could be snow, could be rain. It's going to hit the ground or trees or whatever it hits, and then it's going to do something. It will evaporate. It could go into the soil, right? Those are kind of our two general fates. If the soil is too filled with water already, it's too saturated, or if you hit an impervious surface, you're going to move down slope somewhere, right? So gravity still works for us. And so what we like to think about then on this left-hand side is if water infiltrates, it goes into the subsurface, it's going to still move with gravity. Now, largely that might mean down, but typically that also means towards the valley floor. And what we often have in valley floors are stream channels. So for example, we had a big snowstorm, starting Thursday night, Friday morning here, right? But Boulder Creek was still flowing before that, right? Where did that water in Boulder Creek come from? Besides upstream and besides Barker Dam. You can't, that's the easy one, right? But above Barker, there were still inflows coming in. A lot of that water comes from groundwater, okay? Groundwater becomes the stream flow in most cases that we see. Even during the winter, there will be some groundwater coming in. So I want you to keep that in mind for a moment. I realize there are a lot of other arrows on here. This isn't a hydrology class, so I won't bore you with all those arrows. But the point that I do want to make is simply that there's a lot of water that's moving through the ground. And this even happens during the winter, during the snow season. You build up a big enough snowpack. Snow is an excellent insulator, okay? So that ground temperature, you may not have frozen the ground before that snow built up, and therefore you actually have thawed soil underneath. So any melt that occurs during the winter can move, not just hit the ground and stop, or move laterally, move, with gravity. It may actually infiltrate, move into the soil. Now, there's nature's plumbing on the left. Mother Nature sort of gave us this idea. We've been trying to figure it out for a long time. And then, of course, someone wanted to come along, and this is Wayne Pierce's patent for moving water around on hill slopes here on the right-hand side in I think it was 1960 this was applied for, or the patent was given. But in any event, why don't we try to move water around this way, right? So forget Mother Nature on the left. We can do this with pumps and power, and here's our stream, and we're gonna, pipe water up a hill slope. Well, ultimately, when we start thinking about the impacts of climate change, there's going to be impacts to what happens on the left-hand side. Mother Nature's plumbing is not going to operate the same way. And that largely starts with what happens to precipitation. So we can think about that on one level. On another level, the human response to that, from a perspective of wanting to extend our ski seasons, may be trying to make snow. It might be cold enough. We may not get enough of the right weather patterns to give us a big snowpack. how do these two things come together? So let's talk a little bit about that. All right. I'm going to really simplify what happens on the left-hand side here by saying, if I have a hill slope, I can put natural snow on it, right? So there's my hill slope and there's my layer of natural snow on it. But what we often do with snowmaking or creating artificial snow is to recycle, right? We interrupt or change the hydrologic cycle by taking water somewhere, usually down slope, pulling it upslope, so pulling it back up vertically, and then changing its form. So we go from liquid to create snow, right? To go back to a solid phase, and we spread it across the landscape. Now, on one level, you're like, well, okay, so we haven't really changed the hydrologic balance. And maybe that's true at sort of a bigger scale, right? At the scale of a hill slope, we have changed the hydrologic balance because we've added more snow, and that snow may persist a little longer into the summer. But if we move further downstream, like to the state of Colorado, you might say, well, yeah, but all we've done is internally cycled it. We just kind of rearranged it a little bit. Fair enough. When we do this, though, we add some artificial snow. So there's my, unfortunately, yellow snow. I just need to create some color difference. And of course, it's not always layered, right? It may be intermixed, right? But I'm going to make this simple. I'm going to try to use white for natural snow and this orange color for artificial snow, just so we can see a difference in the figures here. So we've got some snowmaking means that we're doing some hydrologic recycling here in a rather unnatural way. And so what we expect from snowmaking is that we have sort of robbed water that was otherwise perhaps moving downstream. We've taken it from somewhere else and put it up on the hill slope. And so when melt occurs, so come May, June, we expect that we're going to have a big flow pulse, right? All of the hill slopes across a watershed are going to melt their snow, and that's all going to move downstream and head to the stream channel, and we're going to get this bump in stream flow. Okay, so I put no units on this, but I do want to indicate that we're starting, usually a water year starts here in the West, October 1st, and it runs through September 30th. So about, I probably drew this a little too far to the right in here, but about May, June is when we should have that big pulse of snow melt occurring. If we add artificial snow, then at the scale of a hill slope, we expect a couple of things. We expect a higher peak because we've added more water, right, to the slope, so more snow to melt. We probably change that peak to be a little bit later, okay? And we probably have a little more high flow occurring for a little bit later in time as well. So all three of those things are indicated here. They're a little hard to see, but if I use my cursor here, here's the increased peak. Here is a little bit of a lag in time, and then here's this sort of higher flow for a later period of time into the year, all right? Okay, so we should be able to go and find examples of this in the literature, right? Boy, the literature is really scant, let me tell you. But the best study I could find is from a colleague of mine, actually, Jamie Shanley, who works for the U.S. Geological Survey in Vermont. And he's been conducting a study with some colleagues at Stowe. Okay, so this is the West Branch here on the north side here. That's Stowe, Vermont. The catchment area is just over 12 square kilometers. And then right next to it is Ranch Brook, and it has an area of 9.83 square kilometers. Pretty similar in size, very similar geology. You can see from the top right there, it's a little hard to see, but that's sort of an oblique looking at the hill slopes. And you can see the ski runs on the right-hand side and no ski runs on the left-hand side, just indicating that we've got this development that occurred within the West Branch watershed, okay? That development largely occurred from about 2000, or pardon me, there was an expansion from 2004 to 2008 that included new runs, new condominiums, a 9-hole golf course, etc. All of these things impact the Mother Nature's plumbing that we talked about a couple slides ago, all right? So the expectation then, because snow is made on these slopes, is that we would start to see some of those things that I identified in the previous slide. This greater peaks of snow melt because we've added more water up on the hill slope, a later peak and a longer duration of high flows. Well, we sort of see that. Okay, let me walk you through this. What they did, the two data that come from the field here are, we've taken the average daily runoff and now we've converted it to millimeters per day. So because these two watersheds are different sizes, they're slightly different, we take the total volume that comes through in a day and we divided by the area. So now we're saying, okay, we've normalized to the area. So the 12 square kilometers are giving us 4 millimeters today, and the 9 square kilometers or 9.83 and the other one are giving us 3.5 millimeters. Okay, so these are just flows. We can compare them now more evenly because we've kind of normalized to just how big they are, these two areas from which the water is coming. So the blue is our west branch, and you can see it peaks higher, and this is where our snow area and other developments are. So that is peaking higher, and the red is Ranch Brook, which is not developed, and you can see it's peaking lower and earlier. And then we do have this third thing happening, which is we keep these high flow conditions a little longer into the summer. In this case, in the Northeast, we're seeing these peaks in sort of late April, early May. It's more customary for us in the West to see those in sort of late May, early June, maybe even into early July some years, depending on the season. The third plot here on the left-hand side, this is just saying what is the West Branch minus the Ranch Brook information for that any given day. So this yellow plot is just looking at the difference. So sometimes one is higher than the other, but most of the time West Branch is greater than Ranch Brook, and so we're in positive territory here. And you can see that is as much as about 4.5 millimeters per day of runoff kind of in here into May or so. All right. Okay, so great. We can actually see that impact. What if this is average data over 20 years of record of studying these two watersheds. What if we strip this down a little bit and look exactly at what happened year to year? Okay, so the green is identifying when these changes occurred in the West Branch watershed. And on the y-axis, what you see here is instantaneous peak flow for the year in millimeters per hour. I know I apologize, the units are a little goofy. This comes straight out of the manuscript. But what we see then is that blue, according to our hypothesis, or what we laid out with our sort of conceptual model a couple of slides ago, is that the blue should always be higher than the red. And if we look closely, that doesn't quite occur. About 9 out of the 20 years, we have blue happening above the red. In other words, the higher flows are coming from West Branch watershed than are coming from Ranch Brook watershed. So the developed one is yielding more water than snowmelt or total flow than the undeveloped one. So that's interesting. So despite what we saw on the previous slide, it's not always consistent, right? We don't always have that same consistency. And then if we look a little closely at now, the y-axis is our water year, going from October on the bottom to September at the top. Now, if you zoom in there, what we should see, we said that the blue should always peak later than the red, right? The blue being the one that's getting the snow making applied. It's got more water to it, more snow, and therefore more melt. And what we see there, so blue should always be higher later in time than red. And we see that from 2000 to 2003, the green circles indicate when they were happening on the same day. Oh, there's a lot of green circles in there. So the shift it's not perfect. It's not always happening the way that we expect. In fact, about 7 out of 20 years follow this expectation of the undeveloped basin peaking before the developed basin, okay? So it's a mixed bag, but hydrologically, if we just go back to this previous slide, all right, we can be okay with our expectations here. When we dive into it with a little more detail, it's not perfect. All right, so there's part of the hydrologic story. One other thing I should say though about the development, I mentioned golf course. I mentioned new condominiums. Those are changes that have impacts far beyond just the snowmaking on the Stowe side of this. So it's not perfect because we can't attribute all of these changes to just the fact that snowmaking is occurring. By the way, they also included a new pond that they use to source water for the snowmaking. So that's part of this as well. So what about the biogeochemical impact? What do I mean about biogeochemistry? What is that? All of our water, even if you go out to Eldo and you go to the springs, the Eldora Springs, and you get that water, it tastes so good, they call it pure. Sure, it's coming right out of the ground. There's a spring there. They bottle it, we drink it, it tastes wonderful. It is not just hydrogen and oxygen, It is not just H2O. There are all kinds of minerals that are dissolved in that. And that's what we call biogeochemistry, or to say that there's a biogeochemical that is somehow part of that water. It is magnesium, it is dissolved silica, it is dissolved potassium, sodium, all kinds of these things. It just works out that that water, and maybe arguably Fiji water and wherever, a number of different spring sources, provide a taste that's really appealing to us, right? It hits the palate just right. In general, if you don't go to the engineering building, the water on this campus is pretty good, right? I mean, it's not, Boulder's water is not too bad to begin with, but I don't know what, I think it's the old pipes. I don't know. I fill up my water bottle in the engineering center. It's awful. So anyway, I try to stay away from that. But so this hydrology, we've recycled the water. What has happened to that water? Okay, so if we are going to catch water, whether it's in a channel or in a little reservoir down at the bottom of the slope, to capture water and then use it to make snow to put back on the hill slope, the one thing I've not seen a study of is that water is not the same as pure like snow coming out of the sky. All right, that has these biogeochemicals in it already. So what does that mean? Are we enriching that? This is actually a question I don't know the answer to, but I'm going to try to convince you that I think it's important and someone should study it. And I'll come back to Aspen folks and see if they want to study it somewhere down the line later. All right. So I'm going to postulate that hydrologic recycled water already has solutes in it and therefore is enriched in a different way than pure snow is when it melts. So artificial snow is higher in solutes, natural snow is lower in solutes, but it's not completely clean. Even snow melt is not just pure H2O by itself. All right, so what do I mean by that? This paper published by Johansson and Henriksen back in 1978 in Water Resources Research was one of the first to really identify what we call the ionic pulse, which is to say that we have snowpack build up, and as it melts, it gets rid of a whole bunch of ions. What are these ions? Snowflakes, when they come out of the sky, they look beautiful, right? But they are capturing pollutants as they come down, right? They are capturing aerosols and so forth. All of that is largely staying on the outside of the ice crystals as they hit the ground and build up a snowpack. So that means that when we melt that water, we are ready to move those solutes out of there because they're on the outside of the snow grains. All right. So on panel A, you can see the buildup of snow, total precipitation. This is from southern Norway back in the 70s. And then on panel B, you can see there was some melt that occurred. So this is from January to February to March to April. There was a bit of melt that occurred in February. There's another little bit that happened in March. And then by April, it was all the snowpack was gone. Okay. So we're going from top to bottom, 0 to 100% on panel B. I'm also going to show you here on panel C, just a moment, I'll reveal it. We'll go from 0 to 100% of the hydrogen ion elated. So let's just hydrogen ions out there. We call it pH when we talk about concentrations of it. So pH 7, if you get that cool alkaline water my son seems to love, that's like pH 8 or 9. That's pH, right? There is a concentration of hydrogen ions there. All right, this is what the flush looks like. In the first, we have less than 20% of our, let me use the pointer here, sorry. We have less than 20% of our water, our snow disappearing, but we have almost 40% of our hydrogen ions leaving the snowpack. Then here we have another little melt event, maybe 10% or so. Boom, another 40% or so of our hydrogen ions leave, okay? And then we flush the rest out with the rest of the snow melt. But most of the water leaves here. Most of the ions or the biogeochemicals leave early in the snowpack. Here's another way of looking at it. They set up what's called a lysimeter. That is a very fancy way of saying that they buried some kind of container that would collect water. So there's snowpack, there's melt water that's collected inside of this thing. They hold it in this lysimeter and they sample it. Every couple of days, it looks like. And so as the melt water increases, so as they melt more and more, the concentration of the ions, in this case, hydrogen, sulfate, and lead, not a great one, but lead's in there. It's in their snow. So what can they do? You see that by the time we get through 25% of the melt, we have had almost all of these biogeochemicals flush out. Okay, this C over CM is basically saying, what is my instantaneous concentration divided by the concentration of the bulk that I had inside of my snow to begin with? So most of it pops out early. A concentration of 1 would say all of it is the same concentration. Clearly, we have this discrepancy, okay? So natural snow has some biogeochemicals to it. We can't ignore that. But I still have this notion that if we take water that's already run through the hill slope and it's got some biogeochemicals in it, things are already dissolved, then now we're putting that back up on the hill slope and we are enriching, all right? Now, this is some really nice work conducted by the Department of Energy, who's all of a sudden very interested in hydrology in the East River, which is by Crested Butte. So they've been studying the hydrologic cycle and biogeochemicals out there for about 10 years now. They moved away from the polluted sites near Rifle to go to a very unpolluted site, sort of in a relative manner of speaking, in near Crested Butte. But what we have here is a natural hill slope, and in the winter, we're seeing this blue, green, and red fluxes. So you don't see any red arrows in the winter, but what you see is green arrows, small arrows pointing down, coming down the hill slope. That is weathering zone water movement. Bedrock water movement is the light blue or cyan arrows. And then the red ones don't exist in the winter. You can see in the spring when snowmelt occurs, we've got red arrows near the surface. So that's soil water moving. The green is weathering zone water moving, and the light blue is this bedrock. So the bedrock's pretty consistent, doesn't change much. There is a bump right here during snowmelt. During spring, the weathering zone flux increases, the bedrock increases a little bit, and the soil water, all of those now are moving down slope. So these are all flows as water moves down slope toward the river that's down here in this valley bottom. When we add all of those up, what we see is this is our big flux time, which makes sense. And here's our other one in 2018. So here's 2017, here's 2018. So these peaks are all coincident in the subsurface. This one, we had a snow drought in 1718 for any of you who were here for that. A little ugly during the winter. And so the flows weren't as high. And so you don't see bedrock respond as much. You don't see soil respond as much. But there's still plenty of water moving through the weathering zone to give us this bump of the total flow that's moving downslope during the summer. Now, what I haven't told you about, before we talked about hydrogen ion, lead, and sulfate, we're going to put all that together and just call it conductivity. So you can go buy a conductivity probe and stick it in the water, and it'll give you a number. And that number is usually in something like micro or millisiemens per centimeter. And all that is basically thinking about an electrical charge. The more of these ions we have floating around the water, the higher the charge is, okay? So if you put this probe into seawater, you'd see about 50 millisiemens per centimeter. This is on the order of 1,000 microsiemens per centimeter. So far, far less salinity and free ions. Okay, so we increase the water. The purple line is now that total flow in the subsurface, and the red, now what you see is, oh look, there are some of those salts. So here, this first bump right here is some of that snowmelt coming through with that ionic flush. And here's another ionic flush right here. And then something else is going on in the summer here or late into the fall that we won't identify, but we're going to focus on just these flushes right here. Okay, so there are ions coming into the subsurface with snowmelt when that occurs. Does that happen on the bottom end? So now let's go to the stream. This is a stream monitoring station that they have down on the valley floor. And what you can see is that the discharge in cubic meters per second is peaking here in late June. And then the peak here is a little earlier, sort of early June. But this is our 2018 SAD hydrograph year. And here's our higher flow year in 2017. Overall conductivity is rising, and then it starts to fall a bit. This is on the right-hand side, the y-axis. You can see the concentrations have dropped. We have lower salinity, but it's dropping because it's becoming more dilute with all of the snowmelt coming in. But still, at the scale of the hill slope, we still saw that increase in the water moving through the soil. Through the soils. All right. So let me take you a little further now. Let's go back to our cartoons here. And what we saw on the hill slope was that a little peak of solute concentration. So this dashed line increases before we have the peak in the stream flow, right? Or the movement of water through the soils in this case. So if we add artificial snow And that artificial snow, so I have a red question mark there, because this is where we jump into the hypothetical land. If we take that artificial snow that already has some solutes in it, and we go and move it across the landscape. Oops. Oh, I pressed the wrong thing. There we go. Okay. So remember, that was our hydrologic response, that orange line. And this might be our hydrologic response from a biogeochemical perspective. So here's the salt pulsing through because it has more solutes that came with the artificial snow that was put on the slope. Okay, admittedly, I'm in hypothetical mode here, but I'm going to tell you why this is important here in a moment. One of the things that I study besides going to Antarctica is the Colorado River. And in particular, we focus on the upper Colorado River, and we're looking at changes in water quality from about here. We go from just below Gore Canyon, we get in a rigid floating sampling platform. It is a cataract, but we'll get to that in a second. And we float downstream and we cover about 20 miles a day, and we work our way over about 3 weeks, sometimes all the way down to Lake Powell. Depends on the year. Really high flows this past season. We did not go through Cataract Canyon. It's a little bit rough. But we can try to put these pieces together and look at what happens what we're doing when we move is we are collecting high frequency water quality data. Every 10 seconds to 60 seconds, sort of depends on the sensor. We collect data and then we get a GPS point, and so as we move, we can map water quality. I'm not going to go through all of the details of that. I'm going to show you one data collection, or two years of data collection with that salinity that we talked about before. Okay, so this is what we might call the hardest working river in the West. It's the 7th largest watershed in North America. This entire basin, it's 640,000 square kilometers. It serves 40 million people. In a large case, it runs, or it supports winter lettuce production down here in Southern California. That water is important to the things that we see in our grocery stores all across the US in the winter. So, however, I recognize that quality of water is second to quantity. Without quantity, you don't care what the quality is, you don't have it. But if you have it, then you start to care about the quality of that water. The farmers down in Southern California do not want salty water. And so part of the challenge that they face is that any salts that go into the upper basin, they don't go away. They keep accumulating as you move downstream. In fact, it gets worse because water sitting in Lake Powell and Lake Mead evaporates, right? It only increases the concentration of those salts that stay behind. We call that evapoconcentration. So we keep adding salts as we move downstream. All right, so what does this have to do with snowmaking? I'm going to focus on this little section right here, which is the section that we typically run each year during high and low flow. And that's what we're going to zoom in on this next slide, which I took from, this is just a screen capture from Google Earth. But you can see that up here below sort of Catamount Bridge, this region up here, this is the Upper C, as we call it. This is the Upper Colorado Recreation Area. It's a new national recreation area. And it's a glorious river. You don't see much water use up there. There's ag, it's really taking water out to either provide to cattle or to grow grass to feed cattle. There's not a lot of crops up here. This is a cold place. It's 8,000 feet or so in elevation. Then we move down after we join the Eagle right here, and we have this, what I call the geothermal canyon, basically going through Glenwood Springs, Glenwood Canyon, pretty interesting space. And then we move out into this region where we're kind of along like Rifle and Parachute. This is substantial gas and oil development. And then we turn this corner and we get into the Grand Valley. Grand Valley water has been removed for a lot of distribution across the valley that eventually is going to work its way back to the river. We also have the Gunnison coming in right here. I forgot to mention also back in Glenwood Springs, we have the Roaring Fork come in. So we've got some major tributaries coming in. And then the river sort of turns away from I-70 right here at Loma, and it becomes a desert river. Very few inputs. It gets pretty warm out there during the summer, quite hot actually, and therefore we could have this evapoconcentration occurring potentially. All right, so what does our floating sampling platform look like? This is my old one. This is a smaller raft than we have now, but this is a cataract, and part of the reason that we specifically looked for a cataract is we didn't want a boat that you had to lean over the side to do sampling, right? So there's a hole cut in the floor right here, so you can go straight down. You don't have to put yourself at greater risk by leaning out over the edge of the boat. We collect samples and put them in this cooler. This is a sample-only cooler. There are no frosty beverages in this cooler, all right? That's a different cooler. And this pole right here just keeps our GPS antenna up high to be able to get the best signal possible. And then off of this arm, we have these sensors that are all collecting data, and they go back to a brain, a data logger. It's in one of these boxes on the side. So we are collecting dissolved oxygen, turbidity, pH, temperature, conductivity, again, that sort of measure of how many free salts we have floating around. And then when we grab samples, we will analyze those, bring them back, filter them, and analyze them for phosphorus and nitrate. All right. So what does it look like? The upper Colorado is beautiful. If you get a chance, I highly recommend spending some time there. It's a pretty neat space. As you start to move further downstream, you start to see more of these white cliffs further downstream. And then even further, as you get close to Moab, you get more of this sort of desert environment, right? These beautiful red walls and some really warm water. The first time we did this was in July of 2018, and it was like 100 degrees out, and the water temperatures were really quite warm, up to 75 degrees in Fahrenheit and so forth. So quite warm. But in any event, we still saw fish jumping. So maybe they were just trying to cool off. I don't know. But then we get a little further down, and it's quite picturesque, right? It's pretty neat. So this is what you call winning in academia. All right. At the state line, where you cross from Colorado to Utah, there is a very important stream gauge there. So here's that low flow 2018 data that I mentioned, and here's the high flow of 2019. We had a big snow year in 2018-19, low snow year in 17-18. And so very low flow for our summer peak there in 2018, really big flows in 2019. So we did our first run in 2018, and I said, ooh, it's going to be a big year. We should really go compare low flow to high flow. So we did that, and we went out there. And what I want to do now is just think about the low flow year being representative of drought conditions, the high flow year being representative of high flow. So 2018, I've changed this a little bit. So now we're looking at the profile of flow over about a 2-week period, 3-week period when we collected these data. So these are all different USGS gauges. We've just taken the average of the flows during those times, and we're going from right to left. This is way upstream of the confluence with the green. So that's what we call zero. And we go 570 kilometers up, and we went almost 500 kilometers down to the end here. So 300, my math seems a little off there. I'm not quite sure what's wrong with that, but in any event, that may be scaled a little bit wrong, the x-axis there. But then this was 395 kilometers in 2019, and this is what the flows look like. So much higher. This is a log scale on the y-axis there. So this is where the Eagle comes in, the Roaring Fork, the Gunnison, the Dolores. Just a ton of water moving through the system in 2019, not as much in 18. All right, so what was the response from a salinity perspective? What does the salt look like? Here's that specific conductivity, a map of it through space during this one particular time in 2018. You can see we start below half of a millisiemen per centimeter, or below 500 microsiemens. We jump up over 1,000 microsiemens, or 1 millisiemen, by the time we get to the end of that profile in 2018. The Dolores, by the way, was a trickle. We pulled into sort of the Dolores mouth, and it was like a 20-meter wide channel with this little trickle coming through it, and we sort of got stuck in the mud. So that big pulse is probably more mud than anything else. But you do see a step up from sort of upstream to downstream at the Dolores right there. And then the Gunnison provides, in some cases, this is the Roaring Fork. The Roaring Fork came in, and we sort of went in and out of its flow before it mixed. So here's its mixed signal with the Colorado as we move downstream. 2019, way lower. So the low flows give us high concentrations relatively of salts. They're not diluted as much as in the high flow years. All right. So the conductivity was much lower in the high flow years than in the low flow year. And the overall increase in conductivity. So I just went from sort of upstream to the downstream end, 0.74 millisiemens per centimeter. So just as the overall jump, and only about 0.15 in 2019 during the high flow year. So I'm going to call this the 1-2 punch of climate change. So less precipitation gives us lower flows, and less snow, meaning we're likely to potentially make more snow, right? And so if we take these little arrows, I'm going to represent those. The arrows around the edges are the snow melt coming into the basin, right? Coming from the mountains that ring mainly the upper basin, right? That's where our highest mountains are. They're going to shrink, right, with climate change, okay? But then snowmaking may produce higher concentrations of salts because we're recycling that water. The water has already come through and picked up some solutes. Now we put it back up and it's going to take another pass and potentially pick up more solutes again. So snowmaking could result in more salt input. Snowmaking, granted, is a very small footprint across this very large basin. But even so, those salts don't go away, right? We've talked about how those accumulators move downstream. So less snow, potentially higher salt concentrations as we make more snow. So those arrows all get bigger instead of smaller, as we did on the previous slide. So the question, do we have a saltier future? I don't know. I don't know the answer to that. I mean, this is something that I really got to thinking about lately, and I'd be curious to think about it some more. I will leave you with one picture of Antarctica and skiing. This is a mountaineer who was working with us for safety on the left-hand side, my PhD student, Anna Bergstrom, a few years ago while we were in the Antarctica. We do ski down some of these glaciers to do our mass balance measurements. You can see on the left, there's this little post right here is where we used to have a mass balance flag sticking up. So we measure our mass balance as we move, but there's no snowmaking down there. We don't have to worry about it down in Antarctica. So with that, I'll end.
Okay, we're going. Dave Newport, I'm the Director of the Environmental Center here at CU Boulder. We are the oldest, largest, most accomplished campus sustainability center in the United States. We're the student staff of about 160 students and 18 professional staff doing all the campus sustainability work here, everything from the student bus to the ski bus, which we'll do about in a minute, and umpteen other things like renewables and so forth. Happy to be here today. Thank you very much for the opportunity to present. We're going to talk about something slightly different than the last presenter, but with a common theme that will emerge, which I'll foreshadow is what are we going to do about all this? As I indicated, one of the things that we operate is the ski bus, and we'll get to that in a moment. And there's first a disclosure that I have to make at the beginning that I made to Frederica when we talked about doing this. I don't ski. Ducking. I grew up playing ice hockey, and so another form of frozen water. So maybe I'm in the club slightly.
Slightly.
And great respect for skiing, but every time I went to ski as a kid, I was always injured from something from hockey, and I'd fall down skiing because I'm not a very good skier and aggravate that injury. And I said, it's not worth it because my whole life turned around. So that's my lack of qualifications to speak of this. Okay, that joke didn't land, but it's still kind of funny. All right, so skiing, carbon, and transport is what we're going to talk about here. I don't have research to unveil, but a perspective and an approach to what we're going to do about it, I hope will become apparent as a result of this. First, in order to satisfy the skiing part, let's see if this will move. And bingo. Skiing. We are at Ski U. How many people here do ski? Students.
Not only students.
Every student's arguing. Well, you're in a great place. Obviously, we're pretty good at it. And in fact, very good at it. The ski team here has won more national championships than any other university, going back to 1954, whenever they started having those competitions and making that happen. A lot of respect for skiing here and a lot of support for it, obviously. And a lot of folks mindful of what some of the impacts of climate change are on that capacity to ski successfully and recruit students that want to do that. So that's my skiing plug. Carbon. Forget whatever this gentleman just told you about carbon. There's really only 3 kinds. Forget your freshman chemistry course. There's only 3 kinds of carbon in the world when it comes to climate change. And they're arranged in scopes. So we're going to talk about that very briefly, and you're going to be an expert in the scopes of carbon, how to count it, understand it, and mitigate it, all in 30 seconds or your money back. For the sake of accounting carbon, we separate it into scopes. This is the international standard promoted by all the international accords, World Business Council for Sustainable Development, et cetera, et cetera. And basically, it's a method of first accounting for carbon emissions, and then through that accounting process, understanding what you need to do to mitigate and reduce those carbon emissions. And so scope 1 carbon, one more thing to say, sorry. The way we lumped it into these categories is really questions of ownership and control. Who owns that carbon? And who owns that disposition of that carbon? So scope 1 carbon, you own it and you control it. Gas in your car. You opt to buy fuel that's got carbon in it. You opt to drive that vehicle or not. You buy whatever kind of vehicle it is, more or less carbon, whatever. You own it. I love scope 1 carbon because it's completely up to you or I, in the case of CU, that has a campus power plant that makes both electricity and steam for this campus to power these lights. Sometimes, right now we're on Excel, and steam, obviously, that heats and cools the building. Scope 1 carbon, good. Look at its relative size. Scope 2 carbon, you don't own it, but you do have almost direct control over it. Example of that might be if these were, as they are now, sorry, lights powered by Excel. We don't own Excel. We don't own the fuel that Excel is burning, but we own ethically how much they burn every time we touch that light switch. They burn carbon in our name directly because of our demand. Okay. So we can't change and repower their plants and all that kind of stuff. But again, it's a matter of our impact on their combustion process that results in carbon emissions. Scope 3, biggest lump, is everything else. It's the supply chain. It's how much carbon is in this thing. I bought this thing. I enabled Apple to build this in my name and sell it to me, and a whole bunch of carbon went into building this, a whole bunch. So I'm empowering them and enabled, it's a sort of psychological word too, but in this case, it's an operational word. I have responsibility in the carbon emissions that came with this product and everything else in our supply chain, both upstream and downstream. What happens to this when it's done? Traded in, goes back, more carbon goes into its remanufacture and harvesting of the precious metals, many in here, as whereas there's a lot of carbon embedded in these, is in the mining of the precious metals that make these things work. Now off the sea floor in the middle of nowhere. So you see the problem. We are the problem. Make no mistake, we are the problem. And until we really wrap our heads around our complicity in this, and I'm not trying to guilt anybody, I'm sitting there as guilty as anybody in this room. But until we wrap our heads around the complicity we have in climate change, we're not going to be able to attenuate it. It's not something we can flip a magic switch and regulate somebody else to fix. We are the fix. And so that is sort of the ground level entry to this conversation. Personal responsibility, and we'll see in a moment, morphs to collective responsibility and collective action. And how do we do that? That's the killer. So with respect to skiing, we talked about scope 1 carbon and scope 2 carbon. So scope 1 carbon, what sort of energy systems are running the ski slopes? That would be carbon that the Aspen folks, and you heard earlier, I believe, from Schindler. Oh, by the way, if you didn't listen to him, get the recording. If there's a recording, this is the master of how we approach this situation. And a man for which I have umpteen respect. And they've done what they can do at many of the ski slopes to power by renewables, the operations of the ski slopes. Power their heating and cooling through other fuels besides fossil-based fuels, et cetera, et cetera. But as we remember from that first graphic, scope 1 carbon is a small drop in the bucket of the carbon that is associated with skiing. Drop in the bucket. This scope 3 graphic you saw a moment ago. Sometimes the scope 3 carbon, the product, the supply chain, can be 10 times the emissions of the combined scopes 1 and 2 for any given activity. Not unusual. And so when it comes to skiing, how many folks drive up I-70 to go see skiing?
Yeah.
Isn't that fun? In a single occupancy
we
vehicle, crowded in there with a zillion other people, in a blizzard many times. Everybody in my center goes skiing. I think I'm the only one who's for reasons disclosed. And come back with stories about how, and we went up, had a great time, and we came back in this horrible blizzard, and there were trucks jackknife on them, and we dodged a truck by death-defying, carbon-emitting, single occupancy vehicle transport to and from this. You guys got an addiction. Let's get real here. That is death-defying. I'm trying to be polite. So, as you can see from this graph, the solution is to get the heck out of the cars and get onto a train. How many trains in Colorado run to a ski slope?
One winter park on Saturdays.
Yes.
Winter Park Express, run by Amtrak. So one slope is, yeah. And it's a lovely ride. But I'm not really gonna, carve into the capacity. We also saw previously that bus is not a bad idea either. There are a couple of buses. The RTT ski bus, so you can ski from here, never own a car or get into a car, go downtown, get on the RTT bus up to Eldora, ski on a modestly nice slope. I'm told, I don't know. It has black slopes. I hear they're scary. And citizens of people go there all the time and bitch that they can't park. Bitch about that. I'm going, this bus, you don't have to park. We operate a ski bus here, just to Icon Slopes. I don't know what that means, but I was told to say it. And that's to sell out every Saturday and Sunday during ski season. And wonderful opportunity to get on the bus, get some extra sleep. Yes, you got to get there at 6 in the morning, but you sleep all the way up and sleep all the way home. And students go with their friends and have a good time. And it's sold out, so book early. We operate this at a cost basis. It's $20 round trip to these places. Shut up. I don't ski, that's a great deal, right? And we'd love to put more, and before COVID, actually, we hadn't any more buses running. COVID kind of upset that apple cart. We're trying to build it back. But still, these things are sort of dropping in the bucket. And then there's, the Snow Stang, which services these other slopes, and that's in our Colorado Department of Transportation operation. So we've got CDOT, RTD, CU, and Amtrak. Those are the 4 carriers, basically, non-single occupancy vehicle trips up. And of course, for the stuff that comes out of Denver, the trains and so forth, you have to go to Union Station, so you get all this. So it's insignificant in addressing the emissions that are coming with travel up I-70 in your single occupancy vehicle, dodging semi trucks that are jackknifed across the road. My wife will say, "What are you, crazy?" She doesn't like accidents. Well, and as a result of all this, I'm getting into sort of the analytical. Here are our goals as a state at mitigating carbon and attaining the state climate action plan reductions. And you can see, well, we're kind of hitting our numbers on these other sectors, but transport killing us. Transport is killing us. And obviously, ski travel has a lot to do with that. So does everything else. don't need, I'm gonna tell you guys that, you know, the highways are full. And we're Americans, we love our cars. I do too, and we take advantage of that. And that sort of belies the cultural ethic that we have towards transportation. And is the underlying cause of this gap that you see in our drive flow here. So what are we gonna do about that? So I assume that you heard from Hal on what to do about it. And cultural change is the biggie. How do we change cultural approaches? How do we, you know, take away this birthright that every American has, that I'm gonna get a car when I'm 16, go driving and so forth, and turn that into collective action to mitigate climate action, climate change. I'm sorry, and there are some practical ways to think about this, but that, like anything to do with climate action, the challenge is daunting, and it is important to understand that what we do as individuals is great, but it is not letting us off the hook. The atmosphere has clearly signaled it doesn't care where the carbon comes from. It doesn't care. It just cares that it's there, and it's going to respond accordingly. Well, it's responses that scientists are showing us, and so forth. So how can we organize collectively? Because single person action is great, but not enough. And you know, this is a challenge. So I want to tell you a story. How many folks have ever ridden on the Skip out here on Broadway? Okay, most popular bus in Boulder. There's a reason. It started back in the 90s, and for the students here, thank you very much for your parents' actions, maybe, because back in the 90s, the students of CU Boulder said, hey, we got this buses running, you know, Boulder wanted to bus up and have more bus connectivity, and we want students to be able to ride on it without having to pay every time. So the bus pass that you all have, and as a consequence, we all have, faculty, staff, allows us to ride on the buses for free. You really pay for it through student fees, but whatever. It's a cheap deal. So City of Boulder wanted to increase this bus ridership, put the Skip here running up and down Broadway, and did so in the early 90s. And then started surveying and looking at, okay, so nobody was riding on the Skip. Well, why not? So survey goes up, why not? Well, it doesn't come often enough. Okay, fine. More buses, less headway. That's called time between buses. Now, why aren't you riding on the bus? Well, I have to walk too far to get to the bus. Okay, fine. And as anybody who's been on Broadway knows, there's a bus stop on every block north and south. So nobody can say that anymore. You can walk down from the hill to Broadway, you can get on the bus stop right there. Now, why don't you ride the bus? It still wasn't there. Well, I really don't like the people who are right. Okay, but now we're getting somewhere. All right. The first two barriers were technical barriers. They were agency. Do you have the ability to ride the bus? Right? Can't be waiting there all day. Right? Can't walk 5 miles to get a bus, but 5 miles you can walk to wherever you're going. So, but now we get to this sort of emotional thing. And so what was the solution? The City of Boulder and CU combined to run every week, back when they had newspapers made out of paper, a full page ad of basically celebrity endorsements. Here are all the pillars of the community, the professors, the business leaders, the student leaders, who are. We've agreed to ride the buses. We're going to read, come on down. We're going to be on the bus and we'd like to see you. And the rest is history. Okay. You can't get a seat on the bus on the Skip now at rush hour. In fact, they run 2 of them in series, going up and down many times. And if you're driving a car, things in my way, and then you think to yourself, oh God, that would be 37,000 cars in front of me if those people were all driving. So moral of the story is, you have to make this thing available. You have to find out what the challenges are and solve for them. And then you can get collective action. And this is social marketing. So, social marketing versus product marketing. What are the differences? You see them. Product marketing wants to sell a widget and do all these other things. Social marketing basically wants to change cultures. Really what it boils down to. How do we change sort of our way of doing business as a nation, as a community, as a group of students? Social marketing is used all the time. We use it all the time in campus sustainability work. And we'll talk about in a minute, a thing called community-based social marketing. How do we ally people into their respective communities and then spawn that action? There's a fabulous book that outlines all of this. It's the Bible of this is written by a professor and Doug McKinsey Moore, who's been here a few times and teaches this stuff. All the folks that work in my shop have taken this course and accredited in this. And there's a methodology that you can learn on how to make this work. Environmental Studies has a professor of environmental psychology, Amanda Carrico, who's fabulous, one of the global experts in this space. And so the question is back to how do we get people onto a bus or the train? Well, we don't have a lot of trains going right now, so bus is probably the target. And how do we, again, understand those barriers and incentives and reduce the barriers and increase those incentives? There's tons of work on this that can scale to that three-legged stool that you saw from Powell on creating culture change. And there's a bunch of science behind this. And the science is counterintuitive. We think so many times that if we just give people enough information about bad behavior X, it will, because they're smart people, and they'll change whatever they're doing so that bad behavior X goes away. Well, it doesn't work that way. And it's simply that's not enough. And okay, well, we look at paying them or all the money they can save or whatever, doing it. People don't respond well to that either. It's a really interesting human quality that we don't want to be guilted or paid into ethical behavior. And that's actually something admirable about people. Really happy to see admirable things in people. And that's one of the things. What we need to do, what we need is some sense that what we're doing is real and can act collectively to create the difference that we all want. And this is actually from Amanda's work, Professor Carrico, and there's bunches of examples. But here's a simple test of littering, essentially, and or graffiti. And those who responded most were the ones who had participated in this collectively and saw that others were participating in this collectively. And so what they did mattered. It wasn't just one lone voice in a crowd of overwhelming odds against them. So changing a culture is a social marketing problem, in my view, and an enormous one, the biggest one we've ever faced, frankly. And in history, you always hear about, when nations are attacked, as we were in World War II and Pearl Harbor and so forth, we acted collectively if needed. Nothing like a unification of a community against a common enemy. We've not perceived that as a culture in terms of climate change. We've not perceived that as a common enemy. So we are not being pulled together. In fact, it's hotly debated. I'm sure you get carved up all the time by the naysayers about climate change research. Oh, it's stupid, right? So we've got a long way to go on this. And the last thing I'll leave you with is another fascinating book that helps bring together this notion of personal action with collective action. And this is written by a professor at UCLA, Maggie Dalmas, who's also a great analyst. This really screws into what are the motivating things that cause people and hence populations to change. And that's sort of outlined in the too small bubble diagram there, that the things that motivate consumers to buy green or to participate in green stuff, and I'm using green very broadly here, sorry, but I know if you put green in something, in front of something, that something gets better. Yeah. And the one that really seems to be the most transferable back to the skip, which is the analogy I always use about this, is status. What did that celebrity endorsement ad do? Oh, I'm gonna ride with all these big shots and all these, respectable people on the bus. I then have status by association with this community. Because at the end of the day, that's what we all want, is to be normal inside of our community. And so I'm suggesting that as we talk about skiing and climate change, that we listen closely to POW about their methodologies for creating that culture change that is absolutely necessary before we are going to have the agency, the ability to have the infrastructure in place to get up the hill without burning a bunch of fuel and contributing to the problem that we are bemoaning in this meeting and the rest of the time. So that's my short and pithy, hopefully, approach to this. And I know we're going to party here for some questions, so that all the smart questions will go to.
We actually have Greg Dingle, who joined us from Australia.
Okay, all right. So, well, good afternoon, everyone. My name is Greg Dingle, Dr. Greg Dingle, Senior Lecturer at La Trobe University in Melbourne, Australia. So today, what I'm going to talk to you about is a continuation in some ways of what Dave just had to tell us. Before I do that, though, just to tell you just a little bit about myself, who I am. I work here at La Trobe University in our business school. I'm a PhD in sport management and climate change. And so my research focus is on climate change impacts on sport and adaptation responses to climate change impacts. I'm also a member of the Sport Ecology group, which some of you may be aware of. And so my focus is climate change and sport, and particularly adaptation. What I'm going to talk to you today is a little bit about some of the research relating, or that's probably most relevant to this community and those interested in alpine skiing. But before we sort of get into some of the research, what I wanted to do was to just introduce some of the key concepts that have emerged out of the climate change science literature over the last few decades. Now, they're easy concepts to get a handle on, starting with climate hazards. Now, climate hazards, I think intuitively, this is a concept that makes the most sense to us. It's just the extremes that nature gives us. Of course, in this case, in an era of anthropogenic climate change, we're talking about hazards that have been given to us by nature, but have been amplified by human activities. Climate scientists tend to divide these hazards into two categories: fast onset hazards and slow onset hazards. And of course, fast onset hazards include storms and cyclones, extreme rainfall, or forest fires in the other extreme. The slower ones we might think of as rising temperatures, which is perhaps one of the ones that's most concerning to those in the skiing community. In countries such as my own, in Australia, we have parts of the country which get very dry, and so drought is a slow onset hazard. Climate impacts is of course what we experience. What are the consequences? What are the effects of these hazards? And we can divide these impacts into two categories again: fast onset and slow onset. So, for example, if you think about a major Australian sporting event or global sporting event, the Australian Open Tennis Championship, a fast onset example is heat stress for tennis players. Of course, the Australian Open is played in January each year. It's the hottest time of the year in Melbourne. And so a lot of the tennis players get very, very hot. And you can see Daniel Medvedev, this is actually a photo from the US Open this year, experiencing some heat stress from higher temperatures. And of course, one of the consequences that tends to flow from heat stress, more so at the community level than at the elite level, is cancelled sporting events. Slow onset impacts, though, might include higher temperatures that are the byproduct of rising temperatures over time, over decades and centuries. And following from that, we might see rising capital costs for infrastructure that has to be adapted or introduced in order to cope with these impacts. And the third concept I wanted to speak to you about today was climate exposure. Now, my argument is that not all sports experience climate exposure, and therefore climate impacts cannot be equal in all sports everywhere. Some sports are more climate exposed than others, and those sports are much more likely to experience significant impacts from that exposure. So generally speaking, we can divide sports into climate exposed and those that are not. So of course, climate exposed sports are outdoor sports. So think about football, athletics, tennis, golf, but of course, winter sports that are done outdoors, which includes alpine skiing. There's a very different position, though, for sports that are done indoors. And intuitively, this makes sense. So think about sports such as figure skating, basketball, and gymnastics. Now, of course, when we're inside a building, part of the built environment, there's a protective effect from climate hazards. And so the impacts that are felt are very, very different, if at all. So what we might conclude from these three concepts and a whole lot of other climate science which underpins that is that maybe we need some sort of basic or simple formula, a heuristic for making sense of these things that we see. Now, I argue a very simple heuristic is when we combine sport with climate hazards, with climate exposure, we get impacts. Now, if you take away the exposure, the impacts are probably not there at all, which is why sports such as ice skating, a typically indoor activity, is in a very different position in alpine skiing. Some of the research that I've done suggests that there are three domains for climate impacts, whether they're fast onset or slow onset, and they are sports people, sports places, and sports organisations. The one that's perhaps intuitively most tangible is sports people. Now, shorter snow seasons is a consequence of climate change. Winters are getting shorter, summer periods are getting longer. And so what that means is that snowpacks have less time to form and consolidate, and therefore we have shorter snow seasons, which means less skiing overall. At some point, that's likely to result in disrupted competition as well. Sports places, higher temperatures mean less snow and less good quality snow. And what that also tends to result in is attenuated or cancelled competitions or even rescheduled competitions if possible. And the third domain of impacts is sport organisations. Now, this is the one that's probably received the least attention in the research literature. However, what's emerging from the empirical work that I've done suggests that there are increased costs for sporting organisations that are climate exposed. So, for example, ski resorts that need to cope with this challenge of higher temperatures, meaning shorter snow seasons, tend to find themselves doing a lot more snowmaking, which results in increased costs, especially infrastructure costs, to provide the snow guns and so on, and the water needed to do that as well. And then, of course, the other problem for a sport organisation is reduced revenues. And if you have a shorter season due to less snow, it's pretty easy to see how reduced revenues might occur. Now, a very simple example of an impact that's felt by those who do alpine skiing is this phenomenon of rising snow lines. Now, this is happening all over the world. Of course, not all mountains are the same height. They're not at the same altitude. And so snow lines, there's a natural variability of snow lines anyway. A lot of the mountains where we do skiing in Australia are at lower altitudes than those in the Northern Hemisphere, such as the United States. But there's a general trend towards snow lines, that is the lowest point down to which snow forms, are rising with the global phenomenon of climate change. So, of course, this has significant impacts for those who are alpine skiers. It means there's simply less snow to ski on. Now, what does some of the research say? Now, some research that myself and some colleagues did in 2021 into the research. We were researching the research, and we did a review of sport climate change research from the period 1995 to 2021. And surprisingly, there are few studies. At the time, we were only able to find about 57 sport climate change studies in that 27-year period. The pace of studies is increased in recent years as climate change has become a much more better understood phenomenon. But in the space of sport and climate change, there really hasn't been much work done. And so what this means is we have little baseline data on sport climate impacts, including those in the ski industry. However, there's been some excellent research done by some of my colleagues, Daniel Scott, Brenda Jones, Ruddy, Steiger and Knowles. And what they've done is really interesting. We'll come back to that in a moment. The study that we did in 2021 identified 5 themes: heat impacts on athletes and spectators across the studies, heat impacts on athlete performance, adaptive responses by sport, which of course means sport organisations, the suitability of cities for events, and this has particular implications for the ski industry. And if you think about the Winter Olympics, venues, there's fewer of them that are suitable, in an era of climate change, and parameters for safe sport. So there's not as much sport climate change research as we might hope for. When we turn our attention specifically to the Winter Olympics, there's a really interesting study done by our colleagues Daniel Scott, Natalie Knowles, C.L. Mal, Michelle Ruddy and Robert Steiger. This is a study published this year, and it incorporated the perspectives of athletes and coaches on the Winter Olympics. It involved 339 coaches and athletes spread across 20 nations. And one of the key findings of the study was that these athletes and coaches were reporting a perception of unfair or unsafe skiing conditions, having increased over the last 50 years. And this is across all nations that have staged the Winter Olympics. Another finding was that 1 to 8, that the number of viable sites for Winter Olympic Games is in decline, or projected to decline, depending on the emission scenarios that we see unfold over the remainder of this century. In a low emissions scenario, we might see up to 8 sites around the world that are viable for the Winter Olympics. In a high emission scenario, which is what we are on track for based on current emissions reporting, we are likely to have perhaps only one site by 2100 that is a viable one for the Winter Olympics. And of course, mixed up in all of this is athletes calling for accelerated climate change action. A second study that I wanted to share with you, again done by some of the colleagues from the previous study, Natalie Knowles, Daniel Scott and Michelle Ruddy, of course, all from Canada. They were looking at athlete perspectives on athlete activism. And so they surveyed 390 elite winter sport athletes and coaches. And the athletes generally saw themselves as advocates rather than activists, and so hence a low-risk approach. These elite athletes typically feared criticism because of their high-carbon travel routines. They were sensitive to criticism that they were part of the problem. And a third key finding of this study was that these athletes, these elite, winter sports athletes, were very frustrated with the lack of action by the international sports organisations and national sports organisations. So that's a little bit of the research. Now, of course, one of the other problems is that, of course, in an era of climate change, we need to change. As Dave pointed out in his presentation, change is not a luxury; it's a necessity. However, a recent report from the United Nations Environment Programme called Too Little, Too Slow, which was a climate change adaptation or climate change adaptation gap report, reporting on the pace of adaptation on a global scale, argued that the climate risks were increasing as global warming increases, and the current adaptation practices fall woefully behind what is required, which of course is a real concern. If you want to find the report, it's Too Little, Too Slow on the UNEP website. I thought I might also share with you another piece of literature that's directly related to the Winter Olympics, and there's a report conducted by the Sport Ecology Group called Slippery Slopes: How Climate Change is Threatening the Winter Olympics, and that was released in 2022 to coincide with the Beijing Winter Olympics. So the report, which was led by Madeleine Orr, Tim Callison, Walker Ross, of course, Madeleine Orr is a Canadian, and Tim and Walker are both in the United States, is a summary report of some of the academic research focused on the Winter Olympics. And it was motivated by the Beijing Olympics coming along at a time when the authors argued there was a flashpoint needed to drive wider conversation, wider debate about winter sports and climate change. Now, of course, one of the things that we learned during the preparation of the report was that some of the venues in the Yangqing cluster were constructed in areas that were protected forests, which involved clear cutting. And so in order to make the infrastructure for the games, these lots of trees had to be cut down, which is really highly undesirable. Another interesting feature of the Beijing Olympics is that for the first time, the Olympics were done with the assistance of 100% artificial snow. Artificial snowmaking is a feature that we've seen in games prior to Beijing. However, it was a necessity for the Beijing Winter Olympics because it was a low altitude site for the games. What we saw with the Beijing Olympics was snowmaking on an industrial scale. 100 snow generators and 300 snow guns. So this was an acceleration and a ramping up of snowmaking compared to previous Winter Olympics. Now, the biggest concern for these games was not so much about energy use. And of course, energy use is problematic. However, the biggest concern was the volume of water that was being used to make the artificial snow. And an estimate that was provided by Business Insider, so speaking to some of the people who are inside the company who were contracted to provide the snowmaking infrastructure, was that the games were going to require something in the order of 343 million gallons of water, which was estimated to be the equivalent of drinking water for around 900 million people. It's a staggering amount of water. Now, what's concerning is that in an era of climate change, this is likely to become the norm. Snowmaking is likely to become necessary almost no matter where we go for the Winter Olympics. Even on some of the higher mountains, it may be necessary, especially in high emissions scenarios later in the century. There's also a trend towards chemically enhanced snowmaking, so where chemicals are used to get the snow to stay as snow, which is also problematic as well. And one of the other concerns reported by a number of winter athletes, Winter Olympics athletes, is around greater injury risk. Artificial snow tends to be harder. There's a greater concentration of water to air in the snow. And so it's a bit more compacted, or a lot more compacted. And so when athletes fall on it, they tend to be more likely to get impact injuries. So just in conclusion, it's worth saying that a recent report from the Intergovernmental Panel on Climate Change argued that climate change risks are accelerating, compounding, and cascading across all domains, which is really concerning. Climate impacts for sport are not equal, and where they are perhaps of the greatest concern are for winter sports. The Winter Olympics as a global event are particularly vulnerable, and associated with those games are likely to be higher environmental impacts. And so what we would argue, and certainly what I would argue, is that accelerated adaptation of the kind that Dave was talking about is needed now on a global scale. On that note, I'm happy to leave it there, Fed.
Thank you very much, all of you. And questions? Brian?
My question is for Dr. Michael Youssef. So I have a question about the structure of artificial snow and how it stores particulates that increase conductivity. So earlier in your lecture, you basically showed how the structure of natural snow causes particles that increase conductivity to go into the system much earlier than the general melt-off starts. So does differing structure in artificial snow cause there to be a larger volume of particulates, but at a more gradual rate? Or
Yeah,
how
that
would
could
you
be.
expand upon that?
I don't know. That's a good question. So I had forgotten to mention this notion that was just brought up, which is a good one, about the chemicals that are used to try to preserve that artificial snow. I had suggested that maybe there would be a bigger pulse that was earlier. There was kind of that orange dashed line. Maybe it's actually bigger and longer in time, because you don't get that flush in the same way. If you're taking the snow crystal itself and it has built into it these impurities, rather than having them on the outside, you're less likely to see that flush and more likely to see it sort of come out as it melts instead. So yeah, that's a great question. Yeah, it'd be a different hypothetical curve there for sure.
I actually have a follow-up question. Have you tried measuring salinity and minerals in, for instance, in the streams coming down from hills that do intensive training in the spring,
No.
like copper?
Yeah.
Because the Romans, when they wanted to destroy a city, they would put salt on the city, right? So, and for instance, in South Tyrol, it's forbidden to use salt. It's no. And why is that? Because the fields where we ski or race are actually farmed during the summer, right? So it would be interesting to see the concentration of salt where salt is extensively used, I'm afraid, for training.
Yeah, I haven't done that, but that is something that I now want to do. Yeah.
Good, I stimulated your yep.
Kevin McDivitt, I think he's coaching at Stevens Pass in Washington. He ran the Mount Hood Timberline training. He had to do incredible research on the salt evaporation at Timberline, Mount Hood, because they were finding the plastic bags down in the canyons. But he had to actually explain at that time, 20 years ago, that the amount of snow diluted it so much, evaporated by the time it got to the Salmon River and the other rivers they were studying was negligible. But that may have changed. That was 20 years ago.
Yeah.
And
Kevin McDivitt?
Well,
Kevin McDivitt.
Yeah, okay.
He's here at Vail at the World Cup.
Okay.
Now they stopped. For instance, what was it, 2 years ago in Monmouth? They would go with knockheads and salt.
Yeah,
Well,
in
spreaders,
Yeah. just everywhere.
yeah.
So that's massive use. Other questions also for Greg, who is in Australia. So by the way, Greg, you're in Australia. It was brutal this summer because all races were cancelled. there were 0 races in Australia this summer. Because of
Yeah,
lack of-
I think one of the problems in Australian ski resorts is that our mountains are actually at a lower altitude than most of the mountains in the Northern Hemisphere. The mountains are just not as high. And so one of the problems that we face is that rising snowline effect is going to affect our mountains and our skiers sooner than it's going to affect those in the Northern Hemisphere. There was a report done by some scientists here a few years ago that projected that by 2050, depending on emission scenarios, we could have 0 snow on any Australian mountains by 2050. And it would be gone, and it would be effectively gone permanently. Yes, if you speak to Australian skiers, they're deeply concerned about what climate change means for this sport.
You had a question on transportation, but
Anyway.
he left, so you can't ask it.
Mhm.
Now, we want to see those results.
Yeah.
I can give you some hints of,
Okay,
or maybe, also comparing Colorado River and those resorts to places in Europe where you do not have salting on the slopes.
You can also go to Jackson, Wyoming. They're not allowed to salt any of the roads because of the wildlife.
I wondered about
So
that. yeah.
like the Snake River that
Mhm.
runs through the town of Jackson and
Yeah.
along that valley. Like it does have a major problem with nutrient pollution, but I haven't heard anything about increased salinity from runoff.
Yeah,
Well,
Yep.
we don't use salt on any of our roads in Colorado anymore. I know when I first moved here 45 years ago, they were using salt, but they are not anymore, are
I
they?
think they're using mag
Good.
chloride. So yeah, it's a mag chloride solution. They get sprayed behind sometimes.
Okay.
I don't know if that's a state decision or a local municipality decision. But I think that it's a little less nasty than sodium chloride, that rock salt that used to come out.
Yes.
Yeah.
Interesting, in South Tyrol, we don't use salt on the roads, on the fields, but we do use salt on the roads.
Hmm.
So that's kind of, I'll have to look into that.
Well, we're doing-
Anybody else? I think you're all cooked. Thank you so much.
Thank you.
That was really interesting.